This is lesson 18 in our Calculus 3 series, Relative Extrema and Saddle Points. Let's start this lesson by recalling some definitions from Calc I. A function f has a local or relative maximum at x equals c if f of x is less or equal to f of c for all x in some open interval containing c. And similarly, f has a local or relative minimum at x equals c if f of x is greater than or equal to f of c for all x in some open interval containing c. And recall that at points of relative maximum or minimum, either the derivative is 0 at that point, f prime of c is equal to 0, or the derivative does not exist at that point. So for example, we have a relative max here. We can see that f prime is equal to 0 here. Same thing at the relative min here, f prime is equal to 0. But here we can see that f prime does not exist. And that still is a local maximum. Now because relative extrema occurs at points that have a derivative equal to 0 or points that have the derivative not existing, we say that x equals c is a critical point of f if x equals c is in the domain and if f prime of c is 0 or f prime of c does not exist. So we first want to locate all the points with these qualities and then test those critical points to see if we do have extrema there. And we note that if f prime is equal to 0, the tangent line to f of x at x equals c has slope 0, which says the tangent line is horizontal. So here we'd have a horizontal tangent line, and here we would have a horizontal tangent line. So to find relative extrema of f, we find the critical points and test them. And in particular, I want to remind you of the second derivative test for relative extrema because this is the kind of thing that we're going to be looking at for functions of two variables. The second derivative test says if the slope is equal to 0 and it's concave down, there's a local maximum at x equals c. If the slope is equal to 0 at that point and the graph is concave down, you've got a maximum. If f prime is equal to 0 and f double prime is positive, meaning it's concave up at that point, then you've got a local minimum. That's this case. If f prime of c is equal to 0 and the second derivative is also 0, then we have no conclusion from this test. So for something like an x to the third or an x to the fourth graph, you're going to have that your first derivative and second derivative are 0 at these points, and so the test is inconclusive. In this case, we don't have any relative extrema, and in this case, we do have a relative max. So in this case, we would have to investigate a little bit further or go to the first derivative test for relative extrema. Now let's take a look at this for a function of two variables. If we have z is a function of x and y, we say f has a local or relative maximum at the point AB if f of xy is less or equal to f of AB for all xy in some open disk around AB. Before we had point C and an open interval, now we have point AB and an open disk around AB. And in this case, f of AB is called the local or relative maximum value. Similarly, for the minimum, we have f has a local or relative minimum at AB if f of xy is greater than or equal to f of AB for all xy in some open disk around AB. And f of AB is then called the local or relative minimum value. So for example, here we have a relative max, here we have a relative min. And similar to the definition of critical point we had for Calc I, here we say the point AB is a critical point of f if AB is in the domain of f and if either the x partial and y partials are both 0 at that point or one or both of those partials do not exist. So let's take a look at the surfaces we have here. We could see that the x partial derivative and y partial derivative are equal to 0, right? These are elliptic paraboloids. We could see that in each direction we've got parabolas and those partial derivatives are equal to 0 at 0, 0. But what would it look like if one of the partial derivatives does not exist? Here we have f of xy equals x squared plus 10 absolute value of y. We could see that this surface has a fold along y equals 0. To get a better view, let's intersect this surface with the plane x equals 0, for example. what we're getting is the absolute value function, right? When x is equal to 0, this is 10 absolute value of y. And we can see that in this direction, in the y direction, this function is not differentiable. So the y partial derivative does not exist. And this is true at any point for which y is equal to 0. Right? Here's y equals 0. At any point along this curve, we're getting that fold. We're getting that absolute value. So at any point for which y equals 0, we're getting a sharp corner. We're getting that absolute value behavior. So the y partial does not exist when y is equal to 0. That gives us a whole line of critical points. Y equals 0, a whole line in our domain of critical points. And that becomes a whole curve along the surface. Whole curve of critical points. Now we said with functions of one variable that if the derivative is equal to 0 at x equals c, then we have a horizontal tangent line. Here, if both partials are equal to 0, we get a horizontal tangent plane. Now that's not happening here because f sub y does not exist. But if we go back up to these two surfaces, we could see that our tangent planes would be horizontal here. Since both partials equal 0 at that point. Now we've seen the idea of saddle surfaces, and let's talk about those types of points. A differentiable function f has a saddle point at AB if AB is a critical point of f, and if in every open disk centered at AB there are points xy in the domain of f with f of xy greater than f of AB, and points xy in the domain of f with f of xy less than f of AB. The point AB, f of AB, is called a saddle point of the surface. So we've already seen the hyperbolic paraboloid, and we know that has a saddle point at 0, 0. If we intersect this graph with y equals 0, for example, we can see that for any point in a small disk around the origin, there's always going to be a function value that's greater than that point. But when we intersect the surface with x equals 0, we could see that in the same disk around 0, 0, we can always find a function value that's going to be less than that. So this satisfies the definition of saddle point. But let's take a look also at f of xy equals negative x to the third minus y squared. It doesn't have exactly that same saddle shape that we've seen before, but let's see that it does satisfy the definition of having a saddle point at 0, 0. If we intersect this graph with the plane y equals 0, we can see that in any open disk around 0, 0, we're going to get function values that are both less than and greater than f of 0, 0. And that right there satisfies the definition of saddle point, because we also have that both the x and y partials are 0 at 0, 0. So we have a saddle point at 0, 0. Now, to find relative extrema and saddle points of a function of two variables, we're going to find the critical points and test them. Same idea that we had with functions of one variable. And we're going to use a second derivative test for relative extrema and saddle points. Suppose f of xy and its first and second partial derivatives are continuous throughout a disk centered at AB, and that the x partial at AB and the y partial at AB are equal to 0. We're going to define d here, this is the discriminant, d of AB, to be the second x partial evaluated at AB multiplied by the second y partial evaluated at AB minus the mixed partial at AB squared. If d is positive and the second x partial at AB is negative, f of AB is a local maximum. If d is positive and the second partial of f at AB is positive, f of AB is a local minimum. If d is negative, f has a saddle point, and if d is equal to 0, the test is inconclusive. So this discriminant d is telling us if the curvature of the surface is the same in both directions. Notice that if fxx and fyy at this point had different signs, think of these as second derivatives showing concavity, right? If in one direction it's concave up and in the other direction it's concave down, so if we had different signs here, then this product would be negative. Here we're squaring something, so this is positive, so we'd have negative minus a positive, which would give us definitely a negative answer, and that would tell us that we have a saddle point. If the curvature is different, we're saying, we would have a saddle point. And D being positive tells us the curvature is the same. So then we just have to figure out, well, is it a maximum or a minimum? And so we look at either the double x partial or the double y partial. It actually doesn't matter which one you're looking at here because they're going to have the same sign if D is positive. So let's see how we could use this. F of xy is equal to x squared plus 4y squared. We want to find all local extrema and saddle points. First thing we're going to do is find critical points, then we're going to test them using the second derivative test. So we need our x partial and our y partial, and we need to set them equal to 0. So f sub x is equal to 2x, f sub y is equal to 8y. And remember that the definition of a critical point said either both the x and y partials must be 0, or one of them doesn't exist. Now, for a polynomial function, our partials are always going to exist and be continuous, so we don't have to worry about the case where a partial does not exist. So the critical points we get are going to be found from setting both of these partials equal to 0. And remember that we need the x partial equal to 0 and the y partial derivative equal to 0 at the same time. So setting the x partial derivative equal to 0, we get x is equal to 0. Setting the y partial equal to 0, we also get y is equal to 0. That tells us 0, 0 is the only critical point. And so now we need to test it by taking a look at D, the discriminant. So we're going to take the double x partial, the double y partial, and the mixed partial. So the second x partial here is a constant function of 2. The second y partial is a constant function of 8. And the mixed partial we see is equal to 0, another constant function. So certainly when we plug in our point 0, 0, we get 2 here, 8 here, and 0 here. So then D is going to be 2 times 8 minus 0 squared, which is 16, and that's positive. Then we take a look at our double x partial at 0, 0, and that's also positive. This tells us we have a local minimum at 0, 0. And we have no other local extrema or saddle points because remember 0, 0 was our only critical point. And f of xy equals x squared plus 4y squared is an elliptic paraboloid, and it just has our minimum here at 0, 0. Let's take a look at another example. F of xy equals x squared minus y squared. I want you to do the same thing, find all local extrema and saddle points. So please pause the video and work on that problem. We start by finding our critical points, which means we want to take our first partials and set them equal to 0. So for the x partial we have 2x, for the y partial we have negative 2y, and we set these equal to 0. Remember we need them both 0 at the same time. So we need here x equals 0 and y equals 0. So again, 0, 0 is the only critical point. So now we have to find D at 0, 0 and see if we can get a conclusion from our second derivative test. Our second x partial is 2, our second y partial is negative 2, and our mixed partial is equal to 0. So again, plugging in our point, we get those constant values, 2, negative 2, 0, and we notice that here we have D is equal to negative 4. D is negative, that tells us we have a saddle point at 0, 0. And we kind of knew that would happen because this is our hyperbolic paraboloid. Let's take a look at another example. F of xy is equal to x to the fourth plus y to the fourth plus 4xy. Again, we're looking for all local extrema and saddle points. We take our x partial and our y partial, and remember that we need our x and y partials to be 0 at the same time. So our x partial derivative is 4x to the third plus 4y. our y partial derivative, 4y to the third plus 4x. Now we need these both 0 at the same time, so we've got to solve this system of two equations in two variables. And how can we do that? I think the easiest way is substitution. So I start with one of my equations and I solve for y. I get y is equal to negative x to the third. And I'm going to sub that into the y here in the second equation. Now I'm going to divide out by 4 just to make it a little bit simpler. Now I have negative x to the third all taken to the third power. That's going to give me negative x to the ninth plus x is equal to 0. So factoring out an x, we have negative x to the eighth plus 1 is equal to 0. So that tells us x is equal to 0 or x to the eighth is equal to 1. Now this is going to be an even root that we're going to take, so we need the positive or negative. This is going to be x is equal to plus or minus 1 here. So we have x is equal to 0, x is equal to plus or minus 1. But now what's the y going to be? Well, keep in mind that the relationship we have between x and y is here. Y is equal to negative x to the third. That's how we were able to solve here for x. So for each of these x values, the corresponding y value is negative x to the third. So when x is equal to 0, the y value is going to be 0. When x is equal to 1, the y value is going to be negative 1. And when x is equal to negative 1, the y value is going to be positive 1. For each of these x values, the y is equal to negative x to the third because that's the relationship we have here between the two. So we have 3 critical points here, and we need to test all 3 of them. So we need to make our computations for the second partials and the mixed partial, and then compute d at each of these points. So here's our first partials again, and let's take a look at our second partials then. Our second x partial is 12x squared, second y partial 12y squared, and our mixed partial here is 4. So at 0, 0, we've got discriminant 0 times 0 minus 4 squared. So we've got a negative 16, and we definitely have a saddle point at 0, 0. D is negative, gives us a saddle point. At 1, negative 1, we get our second x partial is 12, our second y partial is 12, our mixed partial is always going to be 4. That gives us a positive value for d, and we recognize that the double x partial is positive here, so that tells us we have a minimum at 1, negative 1. At negative 1, 1, we get our second x partial to be 12, our second y partial is also 12, and our mixed partial is always 4 here. So d in this case is also going to be positive. Second x partial is also positive. We have another local minimum at negative 1, 1. So we found 1 saddle point and 2 local minimums. Let's take a look at what that looks like. We could see here, this is the point x equals 1, y equals 1, and then the z is equal to negative 2 here. And then x equals negative 1, y equals negative 1, z equals negative 2 is that other minimum point. And we can see that we have a saddle point at 0, 0, 0. And the saddle point we could see by taking a look at the intersection of this surface with the plane y equals x, for example. We do that and we see we've got our curve that's concave up there. And if we take a look at the intersection of this surface with y equals negative x, we could see that at 0, 0 we've got something concave down. So in any neighborhood of 0, 0, we're going to have function values that are above that point and also function values that are below that point. Now I want to compare what was happening here to this example. Let's take a look at f of xy equals x squared plus y to the fourth minus 2y squared. Same idea, we're looking for local extrema and saddle points. Our x partial is 2x, our y partial is 4y to the third minus 4y. Setting these both equal to 0, we get x equals 0 and y either equals 0 or plus or minus 1. Remember that we need both the x partial and the y partial to be equal to 0 at our critical points. So this says that x must equal 0 at all of our critical points. And this is saying that y could equal 0 or it could equal positive or negative 1. So we have 3 critical points here, and we'll test each of those for extrema or saddle points. But just compare this to what happened here. Here we had 2 equations that involved x and y. So in order to set them both equal to 0, we solved for y here and subbed it into the other equation. That told us what possible x values we could get. But we had to respect the relationship between x and y given by this equation as well. So this is how we found the corresponding y values to go with these x values. The situation we have now is a little bit simpler, but I just wanted to point out the difference. So here let's compute our double x, double y, and mixed partials. Our second x partial is equal to 2. Our second y partial is equal to 12y squared minus 4. And our mixed partial is equal to 0. So at 0, 0, d looks like 2 times negative 4 minus 0 squared. That's negative 8, and that's going to be a saddle point at 0, 0. At 0, 1, we get 2 times 8 minus 0 squared. So we've got 16, which is positive. We recognize that our second x partial is positive here, so we have a local minimum at 0, 1. And at 0, negative 1, we have the same d. We have 2 times 8 minus 0 squared. Again, d is positive, second x partial is positive, and we have a local minimum at 0, negative 1. So at 0, negative 1, x is equal to 0, y is equal to negative 1, z we didn't compute, but it's down here, and that's our minimum. At 0, 1, x is equal to 0, y is equal to 1. This is the point down here. That's our minimum. And at 0, 0, we've got a saddle point. Now let's take a look at another example. F of xy is equal to sine of x squared plus y squared. And again, here we want to find all local extrema and saddle points. So taking our x partial, we get cosine of x squared plus y squared multiplied by the x partial derivative of what's inside. That's 2x. So we have 2x cosine x squared plus y squared. Similarly, for the y partial derivative, cosine of x squared plus y squared multiplied by the y partial of the inside function, and that's 2y. So we get 2y cosine x squared plus y squared. And now we need both of these to equal 0 at the same time. So how could that happen? Well, notice they both have the same factor, cosine of x squared plus y squared. So either cosine of x squared plus y squared is going to equal 0, and that makes these both equal to 0, or it's not going to be 0. If it's not 0, then there's only one other way that these partial derivatives can both be equal to 0, and that's if x and y are both equal to 0. So again, we need the x partial equal to 0 and the y partial equal to 0. And we see that they have a common factor of cosine x squared plus y squared. So if cosine x squared plus y squared is equal to 0, then we get what we need. We have critical points there. If cosine x squared plus y squared is not equal to 0, then the only way we could have both of these equal to 0 is if x and y are both 0. And so we have 0, 0 as our other critical point. Now let's examine this set. Cosine of x squared plus y squared is equal to 0. Well, where does the cosine function equal 0? It equals 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2, right? It's all odd multiples of pi over 2. So one way we could write that is to say x squared plus y squared is equal to 2k plus 1 multiplied by pi over 2, where k is an integer. because if k is any integer, this will give us the whole set of odd numbers, and we'll have all the odd multiples of pi over 2. But another way we could write this is in two parts. X squared plus y squared is equal to pi over 2 plus 2 pi k, right, adding any multiple of 2 pi. Or x squared plus y squared is equal to 3 pi over 2 plus 2 pi k, again where k is an integer. And the reason why I'm going to suggest that we write it like this is because we're looking at sign values at these points. And sign is different at pi over 2 than it is at 3 pi over 2, right? Sign of pi over 2 is equal to 1. Sign of 3 pi over 2 is equal to -1. So we're going to see that it's going to be useful to separate these points into two sets. The ones for which x squared plus y squared is pi over 2 plus 2 pi k. The other is x squared plus y squared equals 3 pi over 2 plus 2 pi k. And notice these are circles, right? Because for any k value, this is a constant, and so you have x squared plus y squared is equal to a constant. So these sets are circles of points in the domain, and they're all critical points along those circles. So now we have to test 0, 0 and these circles of critical points to see what's going on. Here are our x and y partials again, so we can compute our second x and second y partials. Don't forget here for these two partials we're going to be using the product rule, right? Second x partial, we need partial derivative of 2x multiplied by cosine x squared plus y squared plus 2x times partial derivative of cosine x squared plus y squared. And so we're here. For our mixed partial, though, we don't need to use the product rule because if we're taking just a y partial here, this 2x is just a constant multiple. Now let's take a look at what's happening at 0, 0. At 0, 0, we get 2 times 1 minus 0, 2 times 1 minus 0, so that's 2 times 2. And here we get 0 for our mixed partial, so that's 2 times 2 minus 0 squared, so that's 4, which is positive. Second x partial is positive, so that tells us we have a local minimum at 0, 0. But what's going to be happening at the other points? Let's take a look at the circles for which x squared plus y squared is equal to pi over 2 plus 2 pi k. We know for all of these points, the sine value is going to be equal to 1 and the cosine value is going to be equal to 0. So the second partial at these points is going to be 2 times 0 minus 4x squared times 1. So for whatever the x value is along the circle, the second x partial reduces to negative 4x squared. And similarly, the second y partial reduces to negative 4y squared. And the mixed partial is negative 4xy. Again, because we have sine equaling 1 at these points. So what does D look like? Negative 4x squared times negative 4y squared minus negative 4xy quantity squared. That gives us a 0. So the second derivative test is inconclusive. And we're going to get similar results for the set x squared plus y squared is equal to 3 pi over 2 plus 2 pi k. The only difference in the computation is that the sign values there are equal to -1. But you'll notice that you'll also get 0 for the computation of D, which means we need to investigate in another way. Let's take a look at the graph to investigate further. Here's our surface. F of xy is equal to sine of x squared plus y squared. I want you to keep in mind that these ridges that you see here are just a product of the computer software, but really this surface is smooth everywhere. And so we can see that from underneath, we can see we have a minimum at 0, 0. We could see that we have maximums at the circles x squared plus y squared equals pi over 2, pi over 2 plus 2 pi, etc. And we have a minimum here at x squared plus y squared equals 3 pi over 2, and we would also have minimums adding multiples of 2 pi to that radius as well. Now I've been saying that we have maximums and minimums here, but let's just talk about how these points along the circles here satisfy the definition of maximum and minimum. Remember that there's a relative maximum at AB if f of xy is less or equal to f of AB in a small disk surrounding AB. And that's what's happening here. All of the points along this circle share the same maximum value, but that's okay because in the definition of a maximum, you have a less or equal sign. And the definition of minimum, you have a greater than or equal sign. So all of these points are in fact maximums. All of the points here are in fact minimums. And that's the last example we'll go through, but I do want to just comment on one of the surfaces we saw above. For f of xy is equal to negative x to the third minus y squared, that was one of the examples of a saddle point that we looked at. It has a critical point at 0, 0, but you're going to find that d is equal to 0. So the second derivative test would be inconclusive for this function. But looking at the graph, we could see that we have a saddle point at 0, 0, 0. Because if we intersect with y equals 0, we can see we've got that x to the third curve that gives us function values both greater than and less than the function value at our point in any small disk around 0, 0. And this concludes our lesson on relative extrema and saddle points.